Are you here? Carolyn is not here. Sonia, Jen. How about Dustin? Dustin is not here. All right. Now I see a couple of you do not have your profile pictures, and actually 4 of you. Okay, and also one of you is using an avatar picture, and then if you have these right here on Wednesday out, if you're in the waiting room for too long, then you know that maybe one of the reasons why you are not admitted is because of your profile picture. Okay. All right, so keep that in mind, because you don't want to waste any time sitting in the waiting room on Wednesday, well, when other students are taking the test. All right. And I admitted you today, so I can let you know one last time about that, because if you log in without a profile picture, you will not be admitted. Okay. All right, so today we're gonna go to chapter 6. I try to finish the lecture as fast as I can, so we can have some time left, so I can answer any questions you have about the test. Okay. And I think on the last quiz, I haven't gone over the prompts on the last quiz yet. So if I have time, I can go over. If not, then I can just do the problems and then post the solutions on Canvas. All right. Okay. So do you have any quick questions for me before I start the lecture for chapter 6?
You wanted me to remind you about theorems 9, 10, and 14 and 15 for 4.6.
About the formulas, right?
Yeah.
Yeah, okay. I'll do that after I lecture section 9, 6.1. Thank you so much, Danny, about that. Okay, great. So let's go to section 6.1. Oh, by the way, how many sections for chapter 6 that I posted the lecture notes for you already? Is it only one section, 6.1?
Yeah, just one.
Just 6.1. Okay, then I have to work on that too. So you have them ready for next week. So chapter 6 involves power series. Okay, so you need to review power series that you learned in calculus 2. All right. So I provided some lecture notes for you, so you can go over the notes. And if you still need to review more, then you go back to your calculus 2. But I cannot spend too much time teaching you calculus 2 again. All right. Okay. So let's go to section 6.1, and I need to make a correction real quick on the partial notes that I gave you. I don't know if any of you caught that, or you even read the notes at all. Okay, so this is what we have. So in 6.1, what you have is, so this is a list of power series or Taylor series centered at 0, which we call Maclaurin series. Okay. So these, it helps a lot if you know by heart. Now, this one right here, there is something missing. So you see the powers here are even. So when n is equal to 0 or 1 or 2 or an increment by an increment of 1, the power here is not square, okay, because it should be 2n. All right, because when n increases by 1, you go from 0 to 2 to 4 to 6 and so on. So please make that correction. It should be u to the 2n. Okay, so I have that right there. So, and then these are the interval of convergence that you obtained when you were in calculus 2. So I gave you a function and I asked you to find a Taylor series center at 0 for this function, and then you would have to find the interval of convergence for that series, and which happens to be this. So we're going to go over the radius and the interval of convergence down here, and you see how long it would take you to get an interval of convergence for each one. Okay, but like I told you during my time in school, there was no such thing as a cheat sheet, right? So and then no graphing calculator, no computer. So we had to remember all of these formulas here, okay, for the test. So back then, we had to figure out a way to help us remember more easily, which nowadays a lot of students are not good at. And I have noticed that students come into my math classes from classes where their professors allow or teachers allow them to use a cheat sheet, which I do not favor of. Okay, it's not good for you. To me, like by giving you a cheat sheet every time, it's like giving you a timetable to use whenever you do arithmetic. Okay, and it's not good. Okay, I do allow cheat sheets, but it depends on the topics and depends on what kind of formulas involved. But the cheat sheet that I said I provide is like I just give them the formulas on the test. Okay, like right here. This is a very basic Maclaurin series that you need to know. That is the function e to the u. So e to the u is like 1 u squared, u cubed, u to the 4th, and so on. In the denominators are just the factorial of the exponents of u. Right here, the exponent of u here is u to the 0 power. So down here is 0 factorial. By definition, 0 factorial is 1. And the power of u here is 1. So down here is 1 factorial. So that is how I remember the e to the u, right? And then once I have that Maclaurin series in expanded form, you guys should know how to write it as a power series. So this is in expanded form, and this is in closed form. Okay, so there are two different forms: expanded and closed, okay, form. So you should know that, right? Now, once you know this, then try to see the relationship between this Maclaurin series and the Maclaurin series for these functions. And notice that for cosine, you know that for cosine is just all the even terms of e to the u, you see? So u to the 0, u to the 2nd, u to the 4th, u to the 6th. So cosine, you just take all the even terms, all the terms with the even power of u from the function e, you get those, except the signs alternate. So the first term is positive, negative, positive, and negative. And look at the sign of u. Sign of u is just all the terms raised to the odd powers of e. See, odd powers. And then the signs alternate, just like the cosine. All right. And then for hyperbolic cosine and hyperbolic sine functions, so for hyperbolic cosine, they are just all the even terms and all positive. And the hyperbolic sine are just the sum of all the odd powers, you see? So you have that. So now for the hyperbolic cosine and hyperbolic sine, how do you know let's see, what do I want to say? No, never mind. For tangent inverse, so tangent inverse, they are just like the sine of u, or if you just use the e to the u. So for the tangent inverse, it is just the sum of all the terms with odd powers. The signs alternate, but the denominators, you do not have the factorials, just the values, but no factorial. Okay, so you just see the relationship, and if that is something that you were taught to do, and that's what I taught my calculus to do, okay, then it will help you a lot. And then for the ln, see, for the ln, you have ln of 1 plus u. You wouldn't have ln of u because the Maclaurin series for ln of u it doesn't exist, because that means it's centered at 0, and if you have ln of u, and if it is centered at 0, that means when u is 0, but ln of 0 is undefined. So that's why we use 1 plus u instead of u. Okay, and it's just all the powers of the e except the 1, right? Just from u on. Okay, from u on, then you have that, but the signs alternate and no factorial. Okay, and then this one right here, this has nothing to do with e to the u. Okay, so this is, if you want to, you can use that relationship too. But this one right here, basically, the way we obtain this power series is by using long division. Divide 1 by 1 minus u, and you have this. Okay, and then you can just write it in closed form. Now, writing from expanded form in closed form is not easy. Okay, so these power series are easy, but in general, it is not easy to go from expanded form to closed form, and sometimes it is impossible. So it depends on what kind of power series you have. All right. So that's just a quick list, a quick review of a list of common Maclaurin series that you're gonna run into or encounter, okay, in this chapter. Now let's review radius and interval of convergence. So it's just a power series, just like a function, right? So when you talk about a function, we talk about, we need to know its domain, because the domain of a function tells you that the function is defined at those x values in the domain. So for a power series, to talk about an interval of convergence for a power series, that means this interval tells you that the power series is convergent at each x value, or at each u value inside this interval. Okay, so it's acting like the domain of a function. So, but here for power series, we don't call it a domain, but we call it an interval of convergence. Okay, because if a series is convergent, then we know that it has a sum. Okay, because here you're adding an infinite number of terms. So it's not easy for you to tell whether a series has a sum or not, right? Some do, some don't. So if you know a series is convergent over this interval, that means for any u inside -1 and 1, you can always come up with a sum for this series. That means you can add infinitely many terms and you still get a finite value for that sum. All right, so that's what it means by a convergent series. Okay, so let's talk about a general power series. So given a power series center at A, okay, and the coefficient here is c sub n. I like to use the capital C, but I just wrote, the book uses lowercase c, but I might switch it to uppercase C because then it's easier to read and see. All right. So here's what it means by the radius and the interval of convergence for a power series. So if we define I to be the interval of convergence for this series, and R is the radius of convergence, then here's what we mean. Okay, so A is the center, right? So because the power series is centered at A, so A is this value on that interval. Okay. So everything here we call it. So oops. Oh, I forgot to wear my glove. So let me put my glove on. I don't know how long ago you took calculus 2, but everything here is called the interval of convergence. All right, and then the distance from the center out to the right endpoint and also to the left endpoint, that distance is like the radius. So imagine if you have a circle center at A, so from the center go out to the perimeter, okay, or the circumference, that is the radius. So this is the radius. So from here to here is the radius. Okay, so that distance is radius. Okay, so R again is called the radius of convergence. Okay, and I is called the interval. Okay. If the radius is 0, that means nothing here belongs to the interval of convergence. So if the radius is 0, then the interval of convergence is only that value A. Okay. So if the radius is 0, then the interval of convergence is just one value, A. Now, if the radius is infinity, that means the interval is all the way out here to the right and all the way out here to the left of A. So basically, the entire real number would be the interval of convergence. Okay, so if the radius of convergence is infinity, then we say the interval of convergence is all real numbers, right? All real numbers. Okay, and let me do this. Notice that is also defined as this special variable, a letter right there. Okay, that is the set of all real numbers, which is different from the radius capital R. Okay, they are different because this one has an extra line, a segment going down. Okay, now let me see. So if the radius of convergence is equal to some finite value R, that's what it means. Okay, so where R is a finite real number. I know they look exactly the same, but what that means is the radius is equal to a number R. Okay, that's what it means. So if the radius is equal to a finite value R, okay, then there are 4 possibilities. So if the radius is R, that means the interval convergence looks like this, right? But you see, when you have it like this, over here you have parentheses and parentheses. That means the endpoints are not included, but that's not true in general. Okay, so if you know, once you know what the radius is, then you have to check the endpoints to see if the endpoints are included in the interval of convergence. So when you know what the radius of convergence is, then one of these 4 possibilities could be the radius of convergence. So the radius could be the interval of convergence. So the interval of convergence could be this interval right here, not including the endpoints. Okay, so it could be A minus R to A plus R. Okay, or it could be that interval of convergence including the endpoints, or just include the one on the right but not the one on the left. So it could be this, not including the one on the left, but it includes the one on the right. Or it could include the left endpoint but not the one on the right. Or it could include both. And remember, what we are doing here is not differential equations, okay? So this is something that you learned in calculus 2. So how do you know whether the interval of convergence includes the endpoints or not? Well, note, what you need to do is you need to plug each endpoint into the series and find out whether the series converges. If the series converges at that endpoint, then you include it in the interval of convergence. If the series diverges at that endpoint, then you exclude it from the interval of convergence, okay? So whatever, however you want to write on your notes, okay? Then you can just jot it down. Now, one of the tests in calculus 2 that you learned to determine whether a series converges or not is the ratio test. Okay, so how does it work? So the way it works is this. So if I give you a power series in general, so whatever a sub n is, right? So in this case, a sub n is everything here. So a sub n is everything here. Okay, so everything inside the summation symbol is a sub n. So if you have that power series, right, of a sub n, the ratio test says if you take the limit as n approaches infinity of the absolute value of this ratio, and the limit turns out to be some finite value that is less than 1, then the series converges absolutely. Okay, so you need to know the definition of absolute convergence. Absolute convergence is when you take the absolute value of a sub n and the series of that absolute value of a sub n converges. That's what it means. So if the limit of this ratio is some finite real number which is less than 1, then we know for sure that this series converges absolutely. And then there is another baby theorem in that chapter of calculus 2 saying that if a series converges absolutely, then it converges. Okay, so the ratio test tells you or helps you determine whether the series converges absolutely. Okay, and once we know that it converges absolutely, then we know that it converges. Okay, so that is the power series. That is the ratio test. So let's do an example. Okay, so so you have your book. Okay, so I'm going to take my book out. So to save time, I'm going to switch back and forth between the lecture notes and the book. So make sure you open your book and also look at problem 2. That is on page. Okay, it is on page 242. And so it says find the interval and radius of convergence for this power series. So you have this power series. So to find the interval of convergence and the radius of convergence, first, we want to use the ratio test, right, to find out when, to find out where this series converges. Okay, so to do that, we need to identify the a sub n and the a sub n plus 1, and then take the ratio and then put the absolute value around it. So you simplify everything here before you take the limit. All right, so let's do let's figure out what the a sub n is. So a sub n is everything here. So everything here is a sub n. All right, so that's a sub n. So let's just write down. So a sub n, I'm going to write that as okay, 1. I'm going to write like this. Okay. I'm going to write okay. So what is a sub n plus 1? So a sub n plus 1, you just replace n with n plus 1. So that is n plus 1 squared, right? And then if you want to find out the ratio, so you can go to the right. So this will help you. Okay, so you can use these two right here. So that you can simplify. Okay, so a sub n. Okay. So a sub n plus 1 over a sub n, put the absolute value around. It's going to be, so a sub n is x to the n plus 1 over n plus 1 quantity squared. Now, when you divide by a sub n, that is the same as dividing by this. But when you divide by that is the same as multiplying by the reciprocal. Okay. So you just try to simplify as much as you can. All right. So when you simplify this, you see that this and that cancel out. Okay. So what you have now is you have an n squared times x over n plus 1 quantity squared. Okay. All right. So far, so good. And then by the definition of absolute value, you can write like this. All right. Now, n squared over n plus 1 quantity squared. This quotient right here is always positive. So you do not need to use the absolute value. Okay. So this one right here. Okay. Is always positive. So what you have is n squared over, and then now x, we don't know, all right? We don't know. So you better keep x inside the absolute value. Okay, so that is the absolute value of the ratio. So now you go down here and take the limit of that. Okay, so the limit of that is n squared over n plus 1 quantity squared times the absolute value of x. So that is what you have. Now, you are taking the limit. You are taking the limit as n approaches infinity. That means if anything depends on n, you better keep it inside so you can take the limit. But the x here has nothing to do with n. So you treat this one like a constant factor. So basically you can just pull it outside. And then you multiply it by the limit as n approaches infinity. Okay. Okay. Now, from calculus 1, the limit of this one, well, that one you can write that as I'll just keep writing x. It's supposed to be n approaches infinity. That is the same as n over that. Okay. Now the limit as n approaches infinity, n over n plus 1 approaches 1. because that is a rational function and they have the same degree, right? So you just divide by the leading coefficients. 1 divided by 1 is 1. Okay, so you know that this is 1. Okay, so the limit of that of 1 and then 1 raised to the second power, which is 1. Okay, so this limit right here. So that means the limit is the absolute value of x. Okay. So if you want this series to converge, then you want this limit to be what? In order for the series to converge, this limit has to be what?
Less than 1.
It has to be less than 1. Thank you. This has to be less than 1. Okay. Okay, you make a note. If you want the series to converge, okay. So with that said, so here you have, so in order for the series to converge, the absolute value of x has to be less than 1. Now, if the absolute value of x is less than 1, implies x is in between -1 and 1. Okay. So with that said, here's the interval. So you have center at 0, right? Okay. So when you look at the series, you should know that that is center at 0 because that's x minus 0 quantity to the nth power. And then you have 1 and -1. So here's -1 and here's 1. So you know that at least the series converges when x is everything in between -1 and 1. Okay, so from here, you know the radius of convergence is 1, right? Okay, that's the distance from the center out to the end, the right end point. So now, to find out your final interval of convergence, you want to find out whether the series converges at -1 and also whether the series converges at 1. So there are two cases that you have to check. So case I, for x being 1. So let's check the positive value first. Okay, so let's find out. So your series is 1 over n squared x to the n. Okay, so here's what you have. Is it from 1 or from 0? From 1. Okay, so 1 over n squared x to the second power, x to the nth. Sorry. But when x is equal to 1, you just plug 1 in. So what you have is that series. And you just need to remember what you learned in calculus 2. This is called a P series. Okay, where P is 2. P is the exponent of n, is 2, which is greater than 1. So if you have a P series which is greater than 1, then you know the series converges. Okay. So this implies converges. Okay. So you know that the right endpoint is included. All right. But now what about when x is -1? When x is -1, let's plug in. So when x is -1, okay. So if you rewrite, you can write like this. Okay, and this is an alternating series. So if it is an alternating series, you can use the alternating series test. So the alternating series test is like this, right? So you have a series, and it says this series converges provided that it satisfies these two conditions. Condition number one is if you cover the negative factor 1 right here, the factor -1, and the rest is b sub n, right? If you know that the b sub n is always positive, okay, and then the condition number, and then it is also decreasing. That means the bigger the I, the smaller the term is, right? So it is positive and also decreasing. And then 2, the limit of b sub n is 0. So in this case, b sub n is this one. That is b sub n. Okay. So that's the b sub n that we are talking about. So first we need to find out. Okay. So from here, so let's do this. So b sub n is equal to 1 over n squared. So case number 1. So condition 1. Okay. So let me write. Okay. So we know b sub n is 1 over n squared. Okay. And this is always positive, right? For n equals 0, or in this case, n equals starting from 1, 1, 2, 3, and so on. Okay. And also, how do you know that it is always decreasing? Okay. So do you agree that n squared plus 1 is greater than or equal to n squared? For n equals 1, 2, 3, and so on, right? But from here, if you divide, then the denominator on the left-hand side is bigger, so its fraction has to be smaller. Okay. So that implies b sub n plus 1 is less than or equal to b sub n for n equals 1, 2, 3, and so on. So that satisfies, okay, the first condition. So the first condition, you want to make sure that the b sub n or b sub I, it doesn't matter, okay, is always positive. And then you want to make sure that it is always decreasing. Okay. Now the second condition is to take the limit of that and see if it is 0. So the second condition and of course this is 0 when n is infinity. All right, so in this case, you know that series converges. Okay, so by the alternating series test, right? So by the alternating series test, we know that this series converges. Okay, so by the alternating series test.
I have a question, Professor.
Yes.
Isn't the +1 supposed to go inside the square?
Which +1?
You put n squared +1, but isn't it the square of n plus 1?
Let me see. Hold on, let me see. B sub n. Yes, you're right. Thank you.
Welcome.
Okay. So it should be like this. Okay. So this series converges. And you always state the reason, okay, by the alternating series test. Okay, so now you see that when x is equal to 1, the series converges. When x is equal to -1, the series also converges, right? So what is the interval of convergence? So I know I need to one, two. You can find a room, a space for you to write down, but I want to move it down here. Okay. So therefore, the radius of convergence is 1, and the interval of convergence is equal to, or if you want to, you can spell it out, right? So you can spell it out so you remember. So we say the radius of convergence is r equals 1, okay? And the interval of convergence is I equals bracket -1, 1 bracket. All right. And then you box it. Okay. Now, problem 8, same direction. Problem 8 says find the interval and radius of convergence. So you do the same thing. Okay, I'm just, you know, I don't really need to do this, but but I'm gonna do it anyway because this is just a review, and I expect you guys to know how to do that already. Okay, so from here we don't have n, we have k, right? So a sub k is everything here. Okay, so that is a sub k. Okay, so a sub k is 3 to the -k. Okay, so you can write a sub k plus 1. So you just replace k with k plus 1. Okay, so now the ratio is going to be the quotient of these two. So let's just write, okay, 3 negative k plus 1, 4x minus 5 raised to the k plus 1. And down here is 3 to the negative k, 4x minus 5 to the k. Right? And then try to simplify that. So to simplify, you see that this one can cancel out with that one right there. Okay? And then that one right there can cancel out with this one. Oops. Let me use this color so it's easier for you to see. All right. So what you have left is the absolute value of 3 to the negative first power, 4x minus 5 to the first power. Okay, so 3 to the negative first power is a positive number. You can just take it outside of the absolute value. And then here you have 4x minus 5, like that, right? So that is the ratio. So now let's find the limit. So the limit, not k, not n, is supposed to be k. So it is 1/3 times this. Okay. Now, since this expression has nothing to do with k, so it doesn't matter how k behaves. This is always that itself, right? So that the limit of that is just that. And we want this limit to be less than 1 because we want the series to be convergent. Okay, so again, by the ratio test. Okay, so here we can find out what x is. So from here, we know that is going to be less than 3, right? And then, so that gives you 4x minus 5 is less than 3 or greater than negative 3. So 4x is less than 8, greater than 2. So x is in between 1/2 and 2. So let's sketch that. So here is 1/2. And here's 8. I'm sorry, 2. So guess what the center is in this case? What is in between 1/2 and 2?
1.25.
1.25. Okay, so A. How did you get that?
You add them together and then you divide by 2.
You get the midpoint? Okay.
Yeah.
So 0.5, right? Plus 2 and divide by 2. That's the midpoint, right? Because if you take the distance, so 2 minus 0.5, that's 1.5. But if and then you divide it by 2, that wouldn't work, right? Okay, that wouldn't be right there. Wouldn't be at that coordinate. Okay. So imagine you are just trying to find something here so that the distance from here to here is the same as the distance from here to here. So you just take 2 plus 1/2 divided by 2, which is 1.25. Okay. So 1.25. So what is the radius of convergence? It's 0.75. Okay. Now, so you know that at least all the x in here would give you convergent series. Now we have to check the endpoints at 2 and also at 1/2. So for x being at 2, what do we have? So we have the series 3 to the negative k 4x minus 5 to the k. So when x is 2, so when x is equal to 2, 4 times 2 is 8 minus 5 is 3. Okay, so that gives you oh wait, that is not 3 to the negative first, that's 3 to the negative k. Okay, so that is 3 to the 0 power. Okay, you are adding 1 to itself infinitely many times. What do you think the series is?
It's
Is it
divergent.
convergent or divergent?
Divergent.
Okay, but that's like how do we say it? So that's like intuitively, you know, right? You know, because you are adding 1 to itself indefinitely, you're gonna get infinity. Okay, but you know that you cannot, there's no way for you to add 1 to itself infinitely many times and get a value. Okay, so is there a rule for you to show, or is there a test for you to show that this series diverges? So this is a good review. The name of the test is called the test for divergence. Okay, and the test, so if I give you a series, and if you suspect that the series diverges, then you can use this test. Now, how does this test work? The test says, whatever the a sub n is, when you take the limit of that a sub n and it is not 0, then you know the series diverges. Now, if you take this limit of this a sub n and it is equal to 0, you cannot tell. Okay, so here it says. So here is the series. It says if you take the limit of a sub n and it is not 0, then you know the series diverges. Okay, so that is the test for divergence. So let's use that test. So in this case, so you have this k equals 1 to infinity of 1. So that implies a sub k is equal to 1. So that implies the limit as k approaches infinity of a sub k is equal to the limit as k approaches infinity of 1, which is equal to 1, and not 0. Okay, so that's not 0. So what does it mean? Of 1.
Diverges.
Diverges. And you say by the test for divergence. Okay. Okay, so you see, you see when we do this, we have to justify everything that we say. All right. So we know that. So for this interval right here, we're not going to include 2 because when x is equal to 2, the series diverges. So the next question is, what about when x is equal to 1/2? So when x is equal to 1/2, when x is equal to 1/2, that's right over here. So the series k equals 1 to infinity of 3 to the negative k, 4x minus 5 to the k. Okay. When x is equal to 1/2, so 4 times 1/2 is 2. 2 minus 5 is negative 3. Okay, so that's negative 3. And you can rewrite that negative 3 to the k is the same as negative 1 to the k, 3 to the k. Okay. So what do you have? So that gives you negative 1 to the k, and then 3 to the negative k times 3 to the k is 3 to the 0. Okay, so that is that. And then you can use the test for divergence again, because you know that when you take the limit of this one as k approaches infinity, that's not going to be 0. Okay, so right here. So you know that when you take the limit as k approaches infinity of a sub k, okay, that is like negative 1 to infinity, and you know for sure that this is not 0. It could be anything, but we know for sure that it is not 0. Okay, so that means this series diverges by the test for divergence. Okay. All right. So at x equals 2 and x equals 1/2, the given series diverges. So the interval of convergence is just everything inside, not including the endpoints. So therefore, in this case, the radius of convergence is 0.75, and the interval of convergence is 1/2 to exclusively. All right. Oh, why did I write right there? The answer should be written down here. Okay. Any questions? So next, we want to learn how to combine a bunch of power series into one single series, okay? And the only way you can do that is when they have the same starting index value, okay? So if they have the same starting index value, then you can say that that is this, all right? And of course, there are other conditions that we have to check for before we can do that. But in this case, it is this because they have the same starting index. So problem 26, let me see what problem 26 is. Problem 26, it says rewrite the given expression using a single power series whose general term involves x to the k. Okay, so whatever you have in your final answer, you're gonna have x to the k. All right, so let's make a note of that. So we want x to the k. So before we do that, first we need to go to each series right here and convert the exponent of x into k. All right, so here is the exponent of x. We want that to be k, okay? So we're gonna let that be k. So let k be n minus 1. Now, if k is equal to n minus 1, that means n is equal to k plus 1, okay? So we're gonna go over here and convert that power series into something with k. Now, when n is equal to 1, you plug it in, k is 0. So the starting value is 0. Up here, when n goes to infinity, k is going to be infinity minus 1, which is what? What is infinity minus 1?
Still infinity.
Still infinity, right? So you have infinity. And then every time you see n, you replace n with k plus 1. So here's n. You replace k with n with k plus 1. And then I like to use capital letter, okay? C, and then n is k plus 1. And then you have x, n minus 1 is k. Okay, so I just converted the first series into a series with x to the kth power. Now let's do the same thing for the second series. So here's the second series, right? And then you see the exponent is k plus 2, n plus 2. We want that to be k. So we want k to be n plus 2. Implies n is equal to k minus 2. So you go here and you rewrite. So when n is equal to 0, k is equal to 2. When n is infinity, k is infinity plus 2, which is infinity. And then you have c. Now n is k minus 2. And then x2, the k. Okay, so no matter what you're gonna do this week, okay, after the test on Wednesday, make sure you know how to combine series into one series. Otherwise, you're gonna struggle starting next week, all right? A lot of students in the past had a problem combining series into one series. And that's why a lot of them had difficulties solving differential equations using power series. Okay, so I'm just giving you a heads up on what to do here. Okay, so make sure you work on the assignments and study everything in section 6.1 to make sure that you know how to combine series. Okay, so now we're gonna go to the second step and combine them. Okay, so the first series is that. Okay, and the second series you have a 3. I'm sorry, you have a 3. Let's move a little bit to the right. Okay, so you have a 3 here. And then c sub k minus 2 x to the k. Okay, now, so in this case, you know that the two series have the same exponent for x, right? However, in order for us to be able to combine the two series, they have to have the same starting value. In this case, they don't. Okay. So what you have to do is you have to rewrite so they have the same starting value. And to do that, like for the first series, you can just take out the first two terms. So you take out the term when k is 0 and also the term when k is 1. Then from that on, you're going to have k starting from 2. All right, so let's find out. So when k is equal to 0, when k is equal to 0, you have 0 plus 1. So let's plug it in. So 0 for k plus 1, c sub 0 plus 1. So I'm going to do every step for all the steps for you. And then x to the 0 when k is 0, right? And then when k is equal to 1, you get 1 plus 1, c to the 1 plus 1, x to the first power. And then now you have k starting at 2. And then this one right here, you can bring the 3 in. It should be k minus 2. Okay. All right. So let's simplify this one. So that is c sub 1. So this one right here is c sub 1 plus, and what is this? That's 2 c sub 2 x, and then plus. Now for these two right here, they have the same, so they have the same starting value k, right, and the same exponent. That means you can combine them. So that gives you k equals 2 to infinity of, and then, you know, for these two, it's like you're combining like terms, right? They have x to the k in common. You factor it out. So on the inside, you have k plus 1, c sub k plus 1 plus 3, c sub k minus 2, and then you have x to the kth power, like that. So your final answer, so you put everything together. So that's c sub 1 plus 2 c sub 2x plus this series. Okay, and that is k plus 1 c sub k plus 1 plus 3 c sub k minus 2. All right, so that is how you convert, how you combine power series into one series. Now, let's see how we can verify a power series solution of a differential equation. So basically, I give you a power series. and I give you a differential equation, and I ask you, is this power series a solution of this differential equation? Well, just like how you did it before, to verify a solution, you just plug it into the equation. So y is equal to this power series. Now you have to find out what y prime is, so you can plug it in here, and then you combine the two, you see? So to combine the two, you have to know how to do something that we just did here, right? Combining power series. And when you combine the two, make sure you get 0. But before we do that, the first step is to find out all the derivatives so you can plug them in. So here is y. So y prime is the derivative of that power series. And from calculus 1, you know the derivative of a sum is equal to the sum of the derivatives. So you have this. So you just take the derivative of the inside. Okay. Now remember, if anything is related, has x in there, you take the derivative. Anything that doesn't have x, you treat as a constant, right? So this is a constant factor, so you can just pull it out. So what you have is this. Okay, and then you can factor out the -1 to the nth, and here you just take the derivative of x to the 2nth. And the derivative of x to the 2nth is what? Okay. What is the derivative of x raised to a power? The power times x to the power -1. And then multiply by the derivative of x. But the derivative of x with respect to x is 1. So that's it. Okay, so what is y prime? So y prime, if you put everything together, it looks like, so you know that it is -1 to the nth power times 2n x to the 2n minus 1. So that's what you have for the derivative. Now let's plug that in, the differential equation. So the differential equation is 1 plus x squared y prime plus 2xy equals 0. Okay, so let's plug it in. So that means 1 plus x squared. Now y prime is this. Okay, and then plus 2x y. Y is the series. Okay, and then you want to know if that is equal to 0, right? If it is, then you know that the series is a solution. Okay, so let's multiply out. So if you multiply, if you distribute this to this one times that, so you have this series right here. You have that times the series, and then that times the series. So what you have is n equals 0 of -1 to the nth power, 2n x 2n minus 1. I just want to. Okay, and then x squared times. So when you have x squared times, okay, right here. you have x raised to the 2n minus 1 and then times x squared, so you just add, right? So it's like 2n minus 1 plus 2. That gives you 2n plus 1, okay? And then you have this one. You can multiply, you just bring the 2x inside. So bring the 2x inside. So you're gonna have plus n equals 0. And then you have negative 1 to the nth, 2, and then x times x to the 2n is x to the 2n plus 1. Okay. And now, in order for us to combine those three series together, we need to convert the powers, right? So how do you know which power to use? So you have this, you have this, and you have this. Oh, they happen to be the same. Okay, those two. So you look at the one with the lowest power. The one with the lowest power is this one. So you decide to convert this into K. Okay, so you look for the lowest power and you want to convert it into K. So to convert it into K, so that means for this series right here, you want K. You let K be 2n minus 1. Okay. All right. So if that is 2k minus 1, so that means, I'm sorry. No, you want to keep it the same. You wanna do this. You could let it to be 2k minus 1, but you're gonna end up with fractions. You don't want to do that. So you want n to be k. So you just keep this one the same, right? You keep this one the same, and then you want to turn this power and this power into the same power as that. Okay. So let's do that. So so down here, so what we have is the series. Oh wait. I forgot to do something extra. You see right here? What happens when n is equal to 0? When n is equal to 0, the first term is 0, isn't it? Okay, so you know that is the same as 1. Starting from 1, because when n is 0, the first term is 0. So you can just eliminate that. Okay, so I'm sorry. So you want to change this one to a 1, and this is a 1. Okay, because that is from here. So you change this one into. So that is a 1, a 1, and a 1. You see that? So this one right here is a 1. That is a 1, and that is a 1. Okay, so when k is equal to 1 here, so I'm going to use this color so you can identify. So I'm color coding everything here. So that will give you k equals 1 to infinity of that 2k x to the 2k minus 1. All right. So for this second one, how do you know? How do you know what you want? Okay, you want this one to be this guy right here, right? Okay, you want that power to be 2k minus 1. So let me do some scratch work right here for you to see. So you want 2n. You want 2n. Okay, so let me do it on the side here so you can see. You want, so let's do some. Okay, so let's just do some scratch work over here. Okay, so you want the 2n plus 1 to be 2k minus 1, and then when you solve, if you solve for k, so you add 1 over, you have 2n plus 2 equals 2k. So you know you want k to be n plus 1. Okay, so that's what you want. So you go over here, you see, so that will go over here. So you want k to be n plus 1. That means n is equal to k minus 1. So let's go and let's plug into the series. So k, now when n is equal to 1, k is 2. And you still have infinity here. And then negative 1 to the n is k minus 1. And then 2, n is k plus 1, k minus 1, I'm sorry. Okay, and then x to the 2n plus 1, now it is 2k minus 1. All right, and the next series is the same thing. The next series, you want k to be n plus 1 also. So that means n is equal to k minus 1. So your series is going to be n, not n, it's supposed to be k, right? So k equals, when n is 0, k is 1, right? K is 1 to infinity. Negative 1 to the n, so to the k minus 1. 2 x, 2n plus 1 is 2k minus 1. Okay, so equals 0. So you want to know if that is equal to 0, right? Okay, so now that all of them have the same exponents, but they have different starting value. So you want, so this one, you can pull out the first term, so you can have k starts at 2, and you pull out the first term from here, you get k starts at 2. So they match with this. Okay, so let's do that. So I need to write a little bit smaller, so I have everything. Hopefully, I have everything on the same line. So for the power series in purple, I take out one term. So when k is equal to 1, I get negative 1 to the first power, 2 times k, which is 1, and then x to the 2 minus 1, which is 1. All right, and then plus. Now it starts at 2. Okay, and then the next series, it stays the same because you already have k starts at 2. Okay, so the third series, you want to take out the first term. So the first term is when k is equal to 1, you get negative 1 to the 0 power, 2x. When k is equal to 1, you get 1. Right, and then you have k starts at 2. Okay. Wow, it's a lot of writing. Let's see how much. Whoa, okay. So let's try to speed up. I'm writing and speaking too slowly. So what we have is, so that is negative 2x. All right. And then plus, what should I do? Okay. And then this one, let's say plus. Just keep rewriting. I'm going to write faster, okay? The iPad is kind of slippery, so it's hard to write. Okay, and then this one right here is 2x. That one right there is 2x. And then plus okay. Now you see this term and this term. Let me use this color so they can still show the color. Okay, like that. So you see right here, they cancel out. All right. So now you have just these three series, and they have the same exponent. Okay, and then they also have the same starting value. So you can combine. So you can combine the three series. And they all have the same factor x raised to the 2k minus 1. So you can just factor that out. So what you have is negative 1k, 2k for the first series, plus negative 1k minus 1, 2k minus 1 for the second series. And the third series is negative 1k, 2. And then x to the 2k minus 1 on the outside. Right? Okay. So we need to multiply out so we need to simplify this one and see if we get 0, right? But the only way for this series to be 0 is when the coefficient here is 0. So let's do that. Okay, so what do we have? Okay. So we have negative 1 to the 2k. Okay, so here you have negative 1k times 2k. And right here, we can distribute this to that and this to this, right? So what we have is negative 1 to the k minus 1 times 2k. And then minus, when you multiply negative 1, no, this k. Okay, you can either do this or you can use a plus, and that is k, right? Because negative 1 to the k minus 1 times negative 1 to the first power, you add the powers, you get k. And then that is just a 2. Okay. And then plus negative 1 to the k 2. Okay, so let's see what we have here. Okay. No, wait. We don't want to do that. We don't want to do that because we want to be able to cancel with this one. So we want to leave this one as. Okay, let me rewrite. So that is minus negative k to the k minus 1 times 2, like that. Oh, this one is k minus 1. So it's supposed to be k minus 1 here. I wrote k. So please make that correction right there. So that is k minus 1. Okay. So I should separate. Yeah, you see, like, be careful, because when you work with series, if you make one little mistake, oh, that's going to be a lot of time that we wasted. All right, so you see right here, you see this one and this one cancel out, right? So these two cancel out. Okay. What else do we have? Now we want these to be to cancel out also. So we can rewrite this. Okay, so this one we can rewrite. Oops. So now you can see it is very confusing. So for this one right here, you can split it up to -1 times -1 to the k. So -1 means that, and then -1 to the k. Okay. So this one and this one are the same, but you subtract them. So they cancel out. So what you have is zero, okay, so you know on the left side, it is always 0. And that is equal to 0, which is true. Okay, so that's why you say, so therefore, y equals this finally is the power series solution of the differential equation.
Professor,
Yes,
could you scroll up a bit?
is that enough?
Yeah, that's good. Thank you.
Okay,
a little
sure.
more, please. Just like to show that last line at the top.
Right here?
Yeah, thanks.
Okay, yeah, because I need to continue on, okay? So now that you will just learn how to verify a solution. Then the next one, we're gonna learn how to find a power series solution, okay? Now remember, this section is just an introduction to power series solutions of differential equations, okay? When we get into section 6.2 and on, things are getting more complicated. So just like in chapter 4, in section 4.1, it was an introduction, and some of you did not keep up with the pace, and you get lost after that because of all the terminology that I used. Yeah, so make sure you master this section by next week, all right? So problem 36. It's a very simple problem. It says, find a power series solution of the series of the form c sub n x to the n. Okay, for this one, for this differential equation. So you want your power series solution to look like this. All right. Now let's do something that we did in chapter 4. So you know what the solution looks like in chapter 4, okay? Because that's easy, right? So you know so from chapter 4, 4y prime plus y equals 0. In chapter 2, you solve this one by separating the variables, right? But in chapter 4, you rewrite it as an auxiliary equation. You see, like this. I wonder if you notice that after learning chapter 4. Okay, then you know that m is equal to -1/4. Therefore, the solution is equal to a constant e to the -1/4 over x. So you just write -x over 4. Okay, so that is the solution that you got when you use the method that you learned in chapter 4. But here we want to use a power series. Okay, so the power series has this form. So you need to know y prime so you can plug it in. So what is y prime? So the first step is to get y prime. So y prime is the derivative of this series. Okay, so that is just the series of the derivative c sub n and multiplied by the derivative. Okay, so that gives you and the derivative of that is n x to the n minus 1. But when n is equal to 0, oops, come on. When n is equal to 0, you plug it in here, the first term is 0. Okay, so you throw it away. So when n is equal to 1 and on, then you have the terms. All right, so step number 2, you're gonna plug them in. So you have 4y prime plus y equals 0. So that means 4 times n equals 1 to infinity of c sub n times n x to the n minus 1. And then plus y, which is c sub n x to the n equals 0. Okay, so here
For step
I'm sorry?
For step number 1, why do you change the n from 0 to 1?
Because when n is 0, the term is 0. You don't need that term because that is 0.
Okay, I get it. Thanks.
Okay, sure. So now we want to convert them into the same power. So let's say we want to convert them into k. So we want this to be raised to the k power and this one to be raised to the k power. So right here, you want that to be that, right? Okay. And then for the second one, you want that power to be k. So that power is k. So you from here, you can make your substitution. So when n is equal to 1, k is 0. Okay, so k is 0. When n is equal to when k is equal to n minus 1, so n is equal to k plus 1. So that's k plus 1. N is equal to k plus 1. And then x raised to the kth power. So that is my first series. I should have used that, okay? And then the second series, I use green. So k is the same as n, so I just replace k with n with k. All right, so now that they have the same exponent for x, but they do they have the same starting value also? Yes, right? Okay, so we can move we can move the 4 inside and then we can just combine. So we have 4 c sub k plus 1, k plus 1 plus c sub k, and then x to the kth power. Okay, so this is where you need to understand, okay? In order for the left-hand side to be 0, you want this one to be 0, because if x was 0, then, then you get a trivial solution, right? If x was 0, okay? So we want to find a non-trivial solution. So we want that to be 0. So this series is equal to 0 implies the coefficient is equal to 0, and make sure you indicate the values for k. So where k is equal to 0, 1, 2, 3, and so on. So now you have to find a bunch of coefficients. Okay, so from here, let's get the formula. So you know c sub k plus 1 is equal to negative c sub k over 4 times k plus 1. All right, so you plug in one value at a time. Okay, so I'm going to go over here. I say when k is equal to 0 implies c sub 1 is equal to negative c sub 0 over 4. All right. When k is equal to 1, you plug into the formula. So this is a very important formula that you want to come up with. Okay, so this formula right here, we call it a recurrence relation. And so we use that to generate your c's. So when k is equal to 1, that's c sub 2 minus c sub 1 over 4 times 2. Okay, and then since you know c sub 1, you know c sub 1, so here's what you have. So you have 4 over 2 here, and then c sub 1 is equal to negative c sub 0 over 4. Okay, so you have, so that implies c sub 2 is equal to positive 1 over, and you know we want to keep it in this form, and the reason is we want to find a pattern. Okay, so we can write the c sub n, right? Because you see, you want to know what c sub n is. Most of the times it's hard to do that, but if it is easy, then you can write in the form, and I will tell you more about this later on. Okay, so now you go to c sub 2. So k is equal to 2. So k is equal to 2, you get c sub 3 minus c sub 2 over 4 times 2 plus 1 is 3. So you have this. So that is 4. And c sub 2 is equal to 1 over 4 squared times 2 c sub 0. Okay, so what do you have? So c sub 3 is equal to 1 over 4 cubed times 3 times 2 c sub 0. So everything is in terms of c sub 0, because this is the first order differential equation. You're supposed to have only one constant in your answer, and that constant is c sub 0. Okay, so let's do one more and we can get the pattern. So c sub 4 is equal to negative c sub 3 over 4 times 3 plus 1, which is 4. So what you have is 1 over 4. We don't want to multiply those out, okay? And then c sub we're supposed to have a negative here, right? Supposed to be negative because you have a negative here. Okay, so should okay. And then negative there. So you have negative 4 cubed times 3 times 2 C naught. So that means C sub 4 is equal to positive. And then you have 4 cubed times the one of the 4s, you get 4 to the 4. And then you have 4 times 3 times 2, C sub 0. So now let's go over here and you look at all the C's. Okay, so you see that the coefficients alternate in signs, right? So as you do this, then the question is, what is C sub n? So you know that they alternate in signs, right? They alternate in signs. So you know, so C sub n is equal to -1 raised to a power, okay? Oh, sorry. And then you have 1/4. So you see the 4 raised to the power that matches the subscript, you see? So it should be 4 to the n. And this is 4 times 3 times 2, which is 4 factorial, right? And this is 3 times 2, which is 3 factorial. This is 2 times 1, which is 2 factorial. So that should be n factorial, okay? And then C naught. So here for n, let's double check, okay? So check to make sure, or it's supposed to be, you can use C sub k or C sub n, it doesn't matter. I use, so let's use n, let's use k, because we've been working with k for this one. All right, so it should be, so C sub k is this, and then 4 to the k times k factorial C naught. For k equals 0, because the series start from 0. Okay, so 0. Or right here, you use the k here, 0. Okay, so you can check. So let's check. When k is equal to 0, make sure you get, when k is equal to 0, you get C sub 0. Right? So 1, 1, 1, so that's C sub 0. When k is equal to 1, then make sure you get negative C naught over 4. So it should work. All right. So therefore, once you have that, the power series solution is y equals. So since we use n, right? So C sub n is actually -1 to the nth power. Okay, and then so that is your C sub n, and then x to the nth power. Okay, or you can simplify everything here, so it looks like this: 1 over n factorial. That is negative x to over 4. Okay, and that is indeed.
You still need C sub 0, right? Or does that go away?
Yeah, C sub 0 on the top. C sub 0 should be on the outside.
Okay.
Because it is a constant. You can leave it on the outside, or okay, so you can write like this. So y equals C sub 0 because it is a constant factor. And so that is indeed C sub 0 e to the negative x over 4. See right here, this is e to the negative x over 4. If you look at the Maclaurin series up there, that's what it is. All right, so it's gonna take you some time for you to absorb the information here, okay? So I don't expect you to know how to do this right away, but at least if you understood everything that I did here, then that is a great sign. Okay, so just try to go over the notes and do the homework. All right. Now, so I guess we don't have time left. So let me stop the share here, and so what I'm gonna do is I'm gonna work on the solution for the last quiz, and then I'll put on Canvas. Okay. Now for the test on Wednesday, let me go over quickly. So there will be 10 multiple choice questions. All right. So 2 points each, just like last time, and then there will be like seven free response questions. Some are short, some are long, right? So long, like reduction of order, right, is long. Variation of parameter is long. All right. So I remember what Danny reminded me, so I remember. Okay, Danny. So I will tell you that. But if you don't mind staying here for a couple minutes, I will tell you more about the test. One thing that you need to remember, so make sure you write this down and pay attention. Okay, so make sure when you use the superposition approach, if I ask you for the form of y sub p, you need to find out what the complementary solution is first, right? Which is the y sub c, because you do not want y sub p to contain any term from the y sub c. Does it make sense? Okay, so let me, you know what? Let me do this. Let me turn on the camera, the webcam from the other laptop, so you can see it now. So you can see two of me. Okay, that's my twin brother. Okay, and then I will go to, so real quick. Now, you know, of course, you're free to leave if you want to. Okay, but I just want to point this out to you real quick. So for the superposition approach, that is 4.3. Okay, so I want to point out a lecture. Is it 4.3, right? It doesn't look like 4.3. What is 4.3? Oh, 4.4 then. Okay. So for 4.4, okay, right here. See, you should always find y sub c, all right? Because if you don't, then whatever you get for y sub p, you assume that it is y sub p, but it is not, because see, like this one, it contains in there. Okay, so just make a note, go back and study example 7. Okay, from 4.4, and make a note. Always find y sub c to use it to check and make sure that y sub p does not contain any term in there. If it does, you have to multiply y sub p by an x, right? And continue and go from there. Okay, so that's one thing I want to point out. And another thing is the variation of parameter, which is section 4. I believe it's 4.6. So for variation of parameter, if you want to use the variation of parameter method, you have to write your differential equation in standard form. Remember, in standard form means the coefficient here is a 1. So if the highest order of derivative term doesn't have a 1 for the coefficient, you better divide that to the other side. Okay, so like this. See, so you have to divide that to the other side. So once you divide it to the other side, then everything on the other side is your f of x. Okay. See, like this. So you make sure that it is a 1 right here and on the right. And then once you have that, then everything on the right is going to be f of x. Now, I told you not to use the formula in the book, right? Okay, but let's go. You can do that if you, but these are actually the formulas in the book, but I get these from this system. So it's okay for you to use that formula if you want to, okay, because it's the same way since it's remote. So it's okay for you to do this, to use this one right here, okay? 9 and 10 or 14 and 15, right? Yeah, or these. It's okay with me now. But for reduction of order, please do not use the formula in the book. Reduction of order. I told you that before. Do not use this formula. And even though I told you guys, but a couple of you were still using it. Don't use this. Just do everything from scratch. Just like how I did it in class. Okay, so see how the example, the author used the formula. Don't do that because you're going to get a 0 when you do that. All right. So go back to the notes and see how you found the y sub 2 by letting y sub 2 be u times y sub 1, and then find the derivative and plug everything into the differential equations. Okay. All right. If you have any questions, you can ask me now. Okay.
So just to be clear, we can use all of the equations in section 4 except for 4.2?
For 4.2? For 4.2, you may not use the formula. I just pointed out, right? Again. So please listen carefully, all right? That do not use the formula in 4.2. Right here, this is 4.2. Do not use this formula. You have to show work. That's for reduction of order. For variation of parameters, you can do it the way that I did, okay? Or you can use the formulas for 3 by 3, which is the third order. Or you can use, you may use these, okay? You may use this. When we come back to normal and we have in-person classes, I do not allow students to use this, all right? So this is remote learning, so I make it a little bit easier for you guys. Okay, so I hope everything is clear. However, in general, on the test, if I give you a problem and I indicate do not use any formula, then don't use a formula, okay? So if I do not mention it, then you may use it. Okay. All right. So I hope you guys spent the past weekend to study for your test, and you have a couple more days to do that. So do so, and then I will see you on Wednesday. Okay. For the test.
Oh, I'm a professor.
Yes.
So just a quick question about the quizzes, right? So
the quizzes, the latest quiz that I haven't gone over.
Oh no, I just have for the quizzes, like we are willing to drop like our lowest quiz score, right? For
I
the
will
final
drop
grade?
3.
Oh, three, okay.
Yeah.
And also for the exam, you said that there's 10 multiple choice and 7 free response, right?
Yes.
Okay, thank you.
Roughly, yeah. For multiple choice, I know for sure there are 10 of them. Okay.
Okay.
Anything else? No? Okay, you have a good night.
Have a good night, Professor.
Okay. Thank you. You too.
I gotta meet up with some people, so I'm gonna head out, Professor. Have a good night.
Okay.